Do you want to wait until the clock gets at 0, or are you ready? I think you're ready, right?
I'm ready. I'm ready. So,
all right,
let's do it.
Yes. So this morning was a little bit chaotic, but now we do actually get to announce the start of the workshop. So welcome all. Welcome to the Neural building. Yeah, this is the day before the conference. Please kick it off, Tobias, in the workshop for scientific machine learning using functional mock-up units. Now I said it correctly.
Yeah, no, it's correct.
Yes.
So, question if this will be less chaotic than tomorrow.
Then tomorrow I have no idea.
So then today in the morning. Yeah. Okay. So yeah, let's get into it. So, welcome for today's workshop. It's scientific machine learning using functional mock-up units. And this is quite a cliffhanger title because there are two very interesting fields coming together, and this is scientific machine learning and functional mock-up units. And the field of research between both, so the overlap is quite new and very, very small for now. And this is because every time I'm attending a conference or something, I need to explain at least one of them. And when attending a very classical engineering conference, almost everyone knows the functional mock-up units are, but scientific machine learning is a really new thing there. And here at the Julia community, I think everyone has at least a rough idea what scientific machine learning is, but maybe these functional mock-up units might be a new thing for you, so I don't know. If both of you don't panic, because we will introduce both, of course. So this is 30 seconds about me. So my name is Thummerer. I'm a doctoral student at the chair of mechatronics at the University of Oxford. And if you are using FMI Julia, you might know this little red tomato over there. So this is my GitHub profile. And last year I told you that I'm working on my PhD. Good news is I'm almost finished, so it's not done yet, but I'm almost finished now. And this guy here is my boss, Mikelsons. He didn't make it in time because of a conflict schedule, but he will attend the conference, so he will be here too. And this, of course, is Julian. Julian is very important because he's supporting a little today. He's giving a beautiful talk on mesh graph nets, so don't miss that. And yeah, he's here to support a little. And my purpose of existence is researching how to get these two terms from a title together. So this means making methods of scientific machine learning applicable in industrial application. And what I need to add here is that everything I'm doing in research is always based on industry-driven research projects. So I love to explore new things and new methods and create new methods, but I'm always standing with one foot in industrial application. So if I'm reading papers and the abstract states, let's assume that our function is continuous and differentiable, and let's assume that our data is smooth and there are no errors, then I'm out basically, because this is a big difference between academic and industrial application. So industrial models are really nasty. They are discontinuous, they are nonlinear, data is full of errors and noise and things like that. So what I wanted to say is that I always have a focus on making methods a little bit more robust for later application. So unfortunately, we need to start a little boring by setting up the notebook. Yeah, no problem. So we just start the notebook and let everything download and compile, because this can take some minutes. And in the meantime, I will give you an introduction on scientific machine learning, functional mock-up units, hybrid modeling, white box and black box modeling. And in the meantime, we let the notebook pre-compile everything. So after that, the hands-on part starts. We are doing a Pluto. We are working with a Pluto notebook for today. So it's a very interactive thing. We can do a lot of things with very little coding. So don't be afraid if you're quite new to Julia. That's not an issue here. And if not, then there's Julian and I to support. So finally, we wrap up what we find out, and yeah, we summarize a little and check what the next steps are, so the current and future work. And after that, you find me hanging around at the conference until Friday. So if there's anything you want to talk about, so just catch me and have a nice talk. So let's get started. So the plan is, as I already told you, to start the Fluido notebook, and then we proceed with the introduction. So if everything goes well, we should be, all notebooks should be ready for the hands-on part. And if not, there's a little additional buffer. So let's get the thing installed. So all instructions are basically on the slide. Yeah, I hope Julia should be installed. So if not, now is the right time to do it. Everything is tested on the Julia 110 on Windows and on Ubuntu. And yeah, we need to install Fluido if you don't have this. And after then, you can paste this link into your open notebook field, and then click run the notebook. And from this point, don't touch anything else. So just let it download and precompile everything, because you know there is this queue included, and every time you change something, this gets pushed to this queue. And yeah, if this queue gets too big, there might be some issues, and you need to restart the notebook. That would not be that nice. So yeah, if you're familiar with Fluido, you can help each other a little. Of course, I'm here to help, and Julia as well. And I think this should be a thing of 5 minutes or something, so that we can proceed with the introduction. So, is there anyone who needs help for now? Or? So, if you're at the point that you click the run notebook code and everything starts compiling, maybe you can give me a short hint, so I have a rough overview of so how the progress is. Okay, thank you very much. So yeah, maybe we just need another 2 minutes in this case. Is there anybody who needs some help? So just raise your hand, and I'm here. So that's why I'm here. So can I ask who's not ready right now? Okay, so let's wait a little. Let's wait a little. Yeah, of course, because it's an online source, you need to check this trust notebook. So I don't know if you trust me, you can click on it. Yeah, sure. Sorry? So it needs some time, so just let it. It will start for a while. So if there are no libraries that we're using today in our pre-installed in the correct version, this may take up to 30 minutes or something. So until everything is precompiled. So after you run the notebook code, just leave the browser, and this will take some minutes. So there are packages that need a little longer for precompiling. So boundary value diffuse, for example, one. So we just need to wait here a little and proceed with the introduction. So how's the progress? Is there anyone not ready now?
Not ready. And the internet is the issue.
Oh yeah, that's something. But the problem is, do you have access to that error? No, because this one is actually a good connection. You can run it as
or
You disconnect from the browser and then then it goes to the page.
And then open the browser.
Yeah.
So is it okay to proceed? So the introduction, because I think you, so it's really only these 3 steps. So I forgot to say that the slides are online and this URL as well. So if you go to the workshop at the JuliaCon homepage, there's the link for the notebook as well as for the presentation slides. So you don't need to make photos, but you can, of course, if you want to.
Well, it fails at the very first cell in the sense that it complains that Mac is not supported.
Oh yeah, but I'm sorry for this. So there's only support for Windows and Linux, unfortunately, because the FMU is not compiled for Mac operation system. And it's, FMUs are basically compiled code, so I will say something about this. It's not working for Mac, I'm sorry for that. So it's only Windows and Linux. So I hope you can enjoy too. Nevertheless. Yeah, the problem is I need a Mac to compile for the Mac architecture, and yeah, I don't have that, so I'm restricted to using Windows and Linux. So, can we proceed, or should we wait another few minutes? Okay, so now, as promised, the introduction. So we dive into scientific machine learning and functional mockup units and hybrid modeling. And of course, we will check out the use case we are working on today. So this is my little introduction to scientific machine learning, explained with some historical inaccuracies. So at the very beginning, or I need a narrator voice, at the very beginning, so there was nothing but sandy desert, and dust, and there were some lots of data. And not only, some data is not good, that's why there's a little break in this one. And yeah, somehow we felt the urgent need to rearrange these blocks in pyramid-like shapes. So this is our models. We want to make the desert look a little nicer. And so we as optimizers, we started to construct our pyramid based on this data, and we had a really hard time. So building models based on data is really challenging and exhausting. So we started praying to the goddess of scientific machine learning, yeah, which might be Julia, I don't know. And we started praying, does it really need to be that hard? And yeah, the goddess answers yes, because there's a universal approximator theorem, and this states that we can build technically any model we want from the data. And even if it's that hard, we concluded that this is somehow weird. So we are proceeding, dear goddess, we don't want to build everything from the data. We actually just want to build a pyramid thing right over there. So the goddess answers, well, in this case, I think I can support. And then she provides us with a brain from scientific computing, which catapults us straight into the 21st century. And our job becomes much more easier because we are now working side by side with scientific computing. And this is somehow the core idea of scientific machine learning. So we take brains or methods, in this case, from scientific computing to make building pyramids or models more easy. And I'm not done yet, so there's, for every story that's out, there's an alternate ending, and after we explain that we just want to build a pyramid thing over there, and the goddess says, oh really, well in this case I can support, she provides us with a model, solid model foundation for our pyramid. So this is nice too. If there's already a foundation, there's less work to do, of course. And this is the idea behind hybrid modeling. So we take an existing model foundation and extend it with some machine learning to reach our goal, building the pyramid in this case. And I'm still not done yet. As you know, humanity was always a little greedy. So we finally asked, yeah, maybe we could have both and the goddess and says, well, yes, here you go, and provides us with scientific computing and hybrid modeling. And this means there's not much work left to do. And yeah, I hope you enjoyed this little storytelling thing. Now we know at least a little bit about scientific machine learning, at least in a somewhat weird context. And in this picture, we even claim that we can do scientific machine learning hybrid modeling both at the same time, which would be a cool thing. But honestly, we only understand what data is, what optimizes, and what this model is. What is actually this hybrid modeling foundation, and what is the scientific computing brain? This is what we will find out very soon. So back to reality. What are we actually working on today? So as you know, preparing such a workshop is some work. And one of the few advantages is that I can pick the use case we're working on today. And every time I see something like this, little robot here, I go like, yeah, what a cute little body, so come on, do something funny. So a little pen, it's little hand, and so on. So like my wife a little when seeing a baby. So this system here we are watching is a selective components assembly robot arm. So in short, a SCARA. But you know, don't need to be scared of this. So in industry, they often have a third translatoric axis. So we have these two rotational joints to drive inside of our operation plane. In industry, they often have a third axis in translatoric direction to do so-called pick-and-place applications. So we pick something and place it somewhere different. And for this little one here, we have a pen to draw and write the things we're interested in. And this system is, by the way, not mine. It's from Alexander Marayan. It's on YouTube, but there are tons of similar videos like this. And this is a really cool system because it's easy enough to understand it within a few seconds. So we are talking about this for a few seconds now. But it's definitely not easy to build a good simulation model for this, as we will see very soon. So this is a workshop. So what are we going to do? What are we going to do today? So as you know, we need good simulation models for almost every step in engineering. So from the design of the system itself to the control design. So we have a control loop here inside of the system, to operation monitoring and the later application, and so on and so on. So our goal for today is we need a very good simulation model of our SCARA. And this means a model that makes good predictions on what is being drawn or written, or its ink consumption, or its energy consumption, and things like that. And we want it to be physically correct, of course, so that it circulates correctly. And because we need to say economic in industrial application, we only have little data, because data requires experiments and prototypes, and therefore always expensive. So we only have little data. And one important thing is that this is only an example for the methods we are doing today. And yeah, this is not restricted to this use case. So you can do this with many other applications too, as I will show you at the very end. So that's our job. Where is this little data coming from? So in general, we are working always with real measurement data. So for today, we take synthetic data, and this is just because I don't have one of these cute things at home. And yeah, that's an issue. So synthetic data is for today. So we have a high fidelity simulation model of this to generate some data. And we start with a little experiment. So we have some measured motor voltages here. So these are motor voltages from the real system. You can see that they are going up and down, and there are some high frequency oscillations right there. The exact quantities are not relevant in this case. So now what happens to the robot if we put these voltages on its motors? So of course the motors start moving, and on the output side we find the following drawing, and it's the letter P. So this is our training data for this little experiment. And yeah, as you know, it's good scientific practice to have some testing and validation data of this training data. So I was really lazy. So I took a very similar signal. So the left part here is completely identical to training data, but there's a little more here on the right side. So this implies that the letter that is being drawn is somehow very similar to the one from the training data. So can you guess? It's a letter very similar, but there's a little additional drawing at the very end. So there are two options, I think. Yay, it's a B. It's unfortunately it's not the R, it's the E, because this looks quite similar. So if you think about this is the bow of the P, this is something that looks very similar to a bow again, so it's the B. Okay, very nice. So one thing is clear. Yeah, there it is, the B. One thing is clear, that a model that is able to make good predictions on a P should also be capable of doing it for a B. And yes, so this seems quite doable because this drawing of a bow is already part of the training data, so the second bow should be doable as well, actually. So on basis of this real robot system here, what do we expect our model now to do? And well, exactly the same, of course. So we want a model that predicts drawings correctly, and that's it. So this is a cool goal. But how can we get there? And this part is from my last year's workshop, but I loved the meme, so I reused it for this time too. So we simulation engineers need to make a tough decision, and this is how do we want to model. So on the one hand, there's physical modeling. So physical modeling is physically correct. So we use equations that were proven over many centuries to describe the behavior of dynamic systems, and this is basically the best tested modeling approach we have. So on the other hand, the problem with physical modeling is that such models are always built on assumptions. So we always build in some simplifications, and therefore there's always a deviation between our data and our physical simulation model. An advantage is that as a consequence of using these physical equations, we have a very intuitive understanding of what the parameters mean. So if you, for example, increase the mass of a body in a multi-body simulation, you have a very good intuitive understanding of how the system will behave now with the change parameterization. And also a very nice thing is that as long as we are not violating the assumptions that we made during selecting the right equations. So in mechanical systems, it's often that we're far away from the speed of light. That's a valid assumption. In many cases, as long as we don't violate these assumptions, we extrapolate quite well. So our system model is valid for a wide range of use cases. On the other hand, there's the data-driven modeling approach, where we parameterize a more or less universal model based on data. And the downside here is that it basically only looks good. So there are no physical guarantees. I will show you in the next slide what that means. Interestingly, this is the big advantage of this approach. We can be as accurate as we want. So if you think of an artificial neural network and you're fitting some data and the neural network converges during training, there's still a deviation, so that's not a problem. So I can just make it a little wider, a little deeper, and train it for a little longer and gain better results. This is a big advantage. The disadvantage is that there's no intuitive understanding of parameters. So there are these nice explanation videos for image processing using convolutional neural networks, but so where the first layer indicates the edges, the second one the shape, and so on. But we, as a human being, have no understanding of what parameter changes cause to our model output. And another problem is that extrapolation is very often bad. So everything is nice as long as we stay in the known data region, but it can drastically become worse if we have new or unknown inputs. And finally, both are modeled by very different domain experts. So physical models are designed by, I call them scientific or physical engineers. So experts that are very good, have a very good understanding of physical equations and physical modeling. But one needs to say that they often have a quite modest understanding in machine learning. And there's the machine learning side, so where we have machine learning experts that are really, really good when it comes to fitting models on data, but they often have very limited knowledge in the physical modeling domain. So now this is the meme I was talking about. The time for our simulation engineers running out, and we need to make a decision now. How do we want our physical system to be modeled? And is it physical or data-driven modeling? And because it's a very traditional way, as I introduced, we will start with the physical modeling approach here. So this is probably the very first job any simulation engineer will do, and this is built-in system for linear differential equations. So handling very large systems, ODE systems, is a bit bulky. So we are using modeling tools for this. They often have a nice graphical user interface, and yeah, we can click together our model, and after we are finished with modeling, we can click on the translate or compile button. Everything gets translated, and we have our ODE system at the very end. So because the focus for today is not on object-oriented modeling, I have a ready-to-use simulation model with me. And this model is, by the way, partly from the Mikelsons Modelica library, which is open source, so thanks for sharing this. So the model for today can easily be subdivided into 5 main parts. So the first is the trajectory. So the trajectory includes what we want to draw. In a technical context, this is nothing but a file with some coordinates in it. So there's the inverse kinematics that compute the angles for the robot axis based on that trajectory. There's the motor controllers. The motor controllers control how the motors, they control the motor angle to drive at the given positions or angles. And then there's the actual motors, and as you can see, there's this control loop here. So we are feeding back the motor angles to the motor controller to gain a position control loop. And yeah, and finally, of course, the robot mechanics. So the actual multi-body system and some joint friction. So what are we missing here is this bad slipstick effect. This one is not modeled. So what is slipstick? Slipstick is if you put a pen on a sheet of paper with some pressure, and you start adding a force in any direction of the paper plane, only a little force, then nothing will happen. So we are just sticking to the paper plane. So only if we overcome a specific threshold, so this is static friction, we will start moving, and this can be very jerkily. So we are surprised as a human being. The linear controller in this thing is a little surprised, so we will do some jerks in this case. So as a function, this model calculates a friction force based on a velocity. And so we have 2 plots here. The red one is the discontinuous case, and the continuous case in blue dashed here. And as you can see, there's this little bad zone in here where we can apply a force and have a friction force that compensates for this force, but we are always at 0 velocity here. So we are able to push this thing without actually going into movement, and this is what slipstick is. So to conclude, yeah, we didn't model this thing. So you can think of this part like maybe we forgot this to model, or maybe we just don't want it to model because it's friction is always a complicated thing in modeling. Or even if we model it, it's very hard to parameterize because you need to keep in mind that there's nothing like a manufacturer data sheet for pen to pencil friction coefficients or something like that. So so this is an issue, and it's not modeled in this case for today. So keep in mind that this is missing. So how can we get a system of ordinary differential equations to Julia? And there are many options. I will only discuss the three most obvious ones. And this is first option is we just write it down. So we can define a function Julia. And yeah, the advantage here is that it's super fast. So it's white box Julia code. We can throw any AD framework we know on this and can do very fast differentiation. And this is all fun until the models become a little larger. So if you think about 1,000 equations, by the way, the model we're using today is 4,500 equations. So it's 405,000 variables, so it's not that much equations. But if you start doing really big models, so models of industrial scale, then this is just impossible. So it would be super annoying to write down all these systems of this size, and super error prone, by the way, too. So this is an issue here. And another little issue is that we basically need to learn a new modeling language. So it's Julia, it's actually a programming language, but we need to learn something new. And there are guys in the industry who don't want to learn new things. So this is unfortunately true. The second option is we have a bunch of modeling languages in Julia. So I think you might know the modeling toolkit, but there's also Modia or Causal.jl, and everything of these work a little different. So we have a high-level modeling language that is human understandable. And after we finished modeling, we just transform this thing into an ODE. And this is, again, very fast differentiable because we stay in white box Julia code. And because we have, for example, in MTK or Modia, the possibility to do object-oriented modeling, we can, for example, use hierarchical structures, or basically all benefits of object-oriented modeling, which makes handling of large systems possible. But we need to say that also in this case, we need to learn something new, and this is the modeling language, actually. So in my opinion, by the way, it's worth it, because once you tried object-oriented modeling, you never want to go back. It's a cool thing. And finally, there's the third option, and this is the functional mockup interface. And yeah, finally, so from the title, what is the functional mockup interface now? So it's a standardized interface for model exchange, code simulation, and scheduled execution of simulation models. For today, the only important thing is that it can be used for exchanging models. So I can design a model in one tool, export it, and use it in another tool. That's what a model exchange FMU is. And yeah, it's platform independent. This means we can work in Windows as well as in Linux today. And it's the standardized models are called functional mockup units, or FMUs. The standard is the functional mockup interface, FMI. The models are the functional mockup units, FMU. The FMI guys are very strict with this to distinguish between both, because they are used for each other. So let's have a look on a very generic ODE system. So it's a little bit more complicated than on the last slide, but there's the input T, some external input U. Also input T is the time, of course. So the state is X, some parameters P, state derivative on the output side, so X dot, and Y for additional outputs. And if we now look at the interface of a model exchange, we can just go through. So there's the state, input sign, parameters, state derivatives, and output. So it's pretty much the same. And yeah, this is cool. And this is not a coincidence. This is the design goal of the FMI, of course. The only difference is that most FMUs don't show these equations, and this is they basically only allow for evaluating the system for different points. And I don't know why this is the way it is. I think it was a little because it complicates reverse engineering if you share models among different companies, because this is all compiled code by code, but I honestly don't know what the exact reason is. For us, this hiding of equations complicates differentiation, of course, if we want to differentiate over the FMU. But we already have some good solutions for this, I think, and we are further working together with the FMI guys and started a new research project to improve this issue. So, important to add is, let's do this really quick. So FMI is not just a standard for model exchange, it's the standard in engineering. So many famous companies use FMI, and it's a method of choice in automotive, avionics, and also a little in health. So it's a big thing. So now we have this nice third option, and this third option is we export our simulation model as FMU and import it into the Julia programming language. And as I already told you, FMI was not designed for high performance partial differentiation, but we are working on that. And this is the little downside. So as we will see today, it's still fast enough. So for many applications, it's fast enough, but one need to admit that it's not as fast as pure white box Julia code. And yeah, you can use yeah. Sure.
One thing I missed is why do we want to use FMI? What are the advantages?
So if you think about modeling industrial scale, so you have very dedicated tools for specific applications, or you have very large models. So one of them, or maybe both, then you can just do whatever. You don't need to change your workflow. So you can say inside the tools you know, and after you're finished with modeling, you just click the export button and work with this model.
So all the existing tools they use at FMI.
Yeah. So any big modeling simulation tool has at least an FMI importer, and most of them also.
What sort of software should I think of? Is it something like AutoCAD or?
So there's a complete list on the FMI on the FMI-standard.org page. I'm working a lot with object-oriented modeling, so this is Daimler and the OpenModelica editor. You both have an FMI import and export. And I'm also, of course, a little curious in the direction of MTK.
Just to give me an idea, is that like mechanics or chemistry?
It's object-oriented modeling in general, so it's multi-domain. We have mechanics, electrical simulation, one-dimensional fluid simulation is possible a little in Daimler 2, and yeah, there are libraries for example, for medical simulation, so like cardiovascular system simulation and things like that. So it's a very big field that they capture.
Thank you.
Okay, no problem. So yeah, we can use that's exactly the point. So we can use the modeling tools we know, and after we are finished with modeling, we just can export the thing. Yeah. By the way, one thing I wanted to add here is that one of my students is working on getting FMUs also imported to MTK. So maybe, who knows, these two things might merge a little in the future, which would be a nice thing, I think. So now we discussed how to get our OD system to Julia. Now that we are here in Julia, how can we simulate this thing? And let's keep in mind that an OD is mapping from a given system state x to a state derivative x dot, and we need to solve for x. So for this, we need an OD solver, and an OD solver is nothing but a very advanced algorithm for numerical integration, actually. And after we solve for that x at t equals h, so the next x, we can just feed this state back right into our OD. This way we gain a simulation loop and we can simulate for as many steps as we want. So how can we use this for FMI? and it's the same thing again. We just replace the ODE by a model exchange FMU, and it's a completely same thing. We can simulate it this way. So now let's check out how our physical model FMU performs. So we put in our P voltage curves, and we find this drawing. So in orange is the prediction of our model. And yeah, so what should I say? Even if we start quite good here, so there's this line from top to bottom. Yeah, it doesn't look good. So we are writing off the paper, but this is my very own fault. It was me that forgot to model the slipstick friction, and my hope was that it would not have that much of an impact, but it obviously has. So next slide. Actually, there's no really need to check this on testing data. However, we will do it for completeness, and it's the same sad thing. So even on a B, it's the same. So at this point, it's important to say that in general, our model isn't bad. So there are a lot of things done right. So the entire forward and inverse kinematics is 100% correct. There's viscous friction modeled for the robot joints, correct. The motor models are correct, and they are correctly parameterized. So everything is 100% identical, but there's this one important thing missing, and this is slipstick friction. And yeah, there are many right things in it, but this doesn't help in this case. So let's check out what else we got in the toolbox. And the question is, can we do it a little better with a data-driven approach? So let's check this out. And we start by using a plain feed-forward artificial neural network. So the job is very easy. I give you some motor voltages as inputs, and I expect some resulting drawings at the output side. And additionally, one needs to do some minor modifications, but that's not the point here. So we will just check out the results. And so it's the same as for the physical simulation model. We put in our voltage curves and check the resulting drawing. And well, yeah, it's not totally bad. So the ANN output again is in orange here. Somehow this at least looks like a P. It's already better than our incomplete physical simulation model. One needs to admit that. And in fact, it's important that we could improve this fit. So if we're using larger deep artificial neural networks and train it for longer, we can have a much better fit than this. But this is not the point here. And the important thing is next slide, again, on testing data. So we put in the voltage curves of our letter B, and this leads to very disappointing results. So as soon as we're leaving this known data region where our P was, the curve does something that just needs to be cut off the plot because we are writing off the paper, basically. Wow, so yeah, let's conclude our first steps with data-driven modeling. And what we find out is that maybe basically this works. So on training data, one need to say, and extrapolation is very bad. So another important thing to add is that we are training fixed time steps in. So into the artificial neural network, if we have input sampled with 1 sample per second, for example, and the outputs are sampled with 1 sample per second. If I want to use another sampling frequency tomorrow, that will lead to very unexpected results. And yeah, as you know, there are multiple ways to do it better. So we can use RNNs or LSTMs or residual neural networks or physics-informed neural networks, but I was allowed to pick one, so I picked my very favorite, and this is the NeuralODE. This is my very favorite because from the perspective of a simulation engineer, the NeuralODE is the most logical machine learning approach ever. So because if you recall how we simulate a system, so we have this given system state and map it on a state derivative and integrate this into the next system state. The idea is now very simple. So we just replace the ODE with an artificial neural network. So this is now not an artificial neural network as an example that predicts a system state, but this is one that predicts a system state derivative. And this is nothing but an artificial neural network that learns for the right-hand side of an ordinary differential equation. So they were introduced in around 2018, I think, and there was a big selling point and also a little challenge. So the big advantage of this approach is that if you want to learn a dynamical system, you don't need to learn dynamics and numerical integration. For numerical integration, you use a method that is far better than any artificial neural network when it comes to numerical integration. This is an algorithmic ODE solver. So this further leads to interesting advantages, like now we can use different step sizes, for example, for solving. We can use dynamic step size control. If we have a very advanced solver, we have even things like dynamic order control to solve this thing. And we can use special solvers for very special applications, like if we have stiff problems, we use stiff solvers, sparse solvers for sparse problems. And the little disadvantage is that this is not as easy to train as a pure artificial neural network, because if we train on this state at xt plus h, we need to differentiate through the ODE solver. And luckily, there are many methods for this, and many or almost every one of them is implemented in a Julia scientific machine learning ecosystem. So thanks for that. That's a good thing. And because we need to differentiate not only one step, but through the entire solution process, and this means from solver step to solver step to solver step. So through the entire solution, the gradient, and we need this gradient for learning that, for training that thing, is very expensive compared to the gradient over a pure artificial neural network. So this looks appealing to simulation engineers. The question is it worth it, because the gradients are so expensive? So that was neural ODE. So on training data, we see that we are already far better than everything from today. So I use the same artificial neural network for this neural ODE, so the same layout as I use for a pure artificial neural network, by the way. So it's the same network layout, and it's still not perfect, but the same applies here. So we can use, we can train it longer, we can use larger networks and gain a better fit. But the really cool thing comes on the next slide, and this is, of course, on testing data. So on testing data, when we want to write the V, we are far, far, far better than the plain artificial neural network. So it looks like the neural ODE at least understood something of the physical process. So the extrapolation here is in blue. And yeah, it's still not perfect, but one can see that the trends and the direction are quite doing well. So let's conclude this. So neural ODEs to work on testing and also on training, and training as well as on testing data, which is cool. And we could do better if we want. And we have some new cool features like dynamic time stepping during the solution process of the neural ODE. And we can even exchange the solver. So we could train the neural ODE with one solver and use another solver tomorrow. Or we can use these cool hybrid solvers from differential equations where we can switch between explicit and implicit methods depending on the stiffness properties of our neural ODE. This is cool. So now, what if we combine the advantages of both approaches? So what if we do data-driven modeling based on a physical model foundation for our pyramid? So we have the explainability, the physical correctness, and the good extrapolation of the physical world here, and pair it with the ability of the data-driven approach to compensate for any deviations between our model and data. So this is a nice idea. How can you do something like this in practice? And yeah, then this is the final read, so we push both buttons. How can we do this in practice? So it's just a drawing. Well, in our drawing, we can just do everything together. So there's nothing that can hold me back from this. So we have our ODE here. There are some interconnecting signals between the ODE and the ANN that could be states, that could be state derivatives, they could be any observable variable. and then there's the ODE solver at the very end. So there are different names for this. So I read hybrid neural ODE. It's definitely a subtype of universal differential equation, or more correctly, it's universal ordinary differential equation. But we needed a term for this for the scaling research project. So we, especially for this thing, so we call this a physics enhanced neural ODE. So coming from the neural ODE point of view, or in short, PEN ODE. So again, if this now works for ODEs, we can also replace this thing with a model exchange FMU. And equipped with FMUs, we can handle very large ODE systems very easy. So we call this resulting structure a NeuralFMU, but as you know, it's nothing but a PEN ODE. So we just replace the ODE with the FMU here. So, and another thing that is important, even if we are using FMUs today, everything we show is fully compliant to ODE systems. So if you want to use symbolic ODEs with the same approaches, you can totally do that. There's nothing that speaks against this. So we are using FMUs today just because the presented system consists of 4,500 variables, and this is very large. So this is nothing that we want to implement by Julia. And by the way, because you asked, this system was modeled in Daimler actually, so we modeled it in Daimler and then we exported this as FMU. So the big question is still for sure, but does this actually make anything better? So for now, it's just like an idea.
Quick question. Sure. Do you have to use ordinary equations? Do other groups maybe use like Markov nets? Like the final.
So you mean in terms of other differential equations or other universal approximators?
Approximate.
So technically both is possible. So I need to admit that at least 90% of what I'm doing is ordinary differential equations, or even more. Because yeah, this is what can be described by a model exchange FMU. You want me to say that model exchange FMUs are for now only suitable for ordinary differential equations. So if you have a partial differential equation, for example, you can apply a spatial discretization to it, and this way you gain again an ODE that you can export. But almost everything I'm doing is ordinary differential equations. But we, at some points, we try other universal approximators, but yeah, I need to admit that in most cases, just the neural networks, so the fully connected forward neural networks, do the job in most cases for us. So we are experimenting a little, but that's the default for us. So yeah, sure.
One question. Let's say from a mathematical point of view, do you say that one part is an ODE and the next part is then the neural network? So the x1 is f of x and x2 equals the neural network? Or?
Yeah. So in most cases, it's so if you because we're speaking from the mathematical point of view, so in most cases the system is an ordinary differential equation. The neural network in this case would be an algebraic equation. So we're connecting these two, but it's a good cliffhanger for the very end of the presentation, because there we will discuss this very short in a little different context by combining arbitrary, call them arbitrary models. So we are not restricted to combine always an ODE and an algebraic equation. So there are different things possible. So yeah, for us, this thing was a game changer. So this is my very favorite little analogy, and in this one we have this plain neural ODE here, and the plain neural ODE is like an antique canvas, and we can basically form this into any dynamic system we want. So we want to train for the dynamics of a train. We can totally do that. And if I want to train something completely different tomorrow, like spreading dynamics of ABC, so this was called in this case, that's totally possible. Both is possible applying the neural ODE methods. So a pen ODE is like a neural ODE with some physical equations in it. And this is, in this analogy, like a canvas with a car sketch on it. So I can train this into a Spark convertible. I can train this even into a thing like a monster truck. But no way that I train this car sketch into a COVID spray dynamics. That's not possible anymore. So, or at least not with an effort I'm willing to do. Yeah, sure.
We have a coffee break. 5 minutes for 10 minutes.
Okay, everything all right. So this will suit well. Thank you. So this looks like a restriction at first glance. So this thing can train for everything, but this thing can only train for very limited amount of solutions. This feels like a restriction, but always restrictions come with benefits. And the big benefit here is that if you give me a drawing of a car sketch, I can do a convertible. So I just removing the top and that's it. So if you give me an empty canvas and say, make me a painting of a train. So my drawing skills are limited to what you see here. So it's much more work. And the same applies to neural ODEs and pen ODEs. So the training is much more intense if we do it with an empty canvas. But it becomes much more easier if we start with a sketch of our dynamic system. And easier to draw here means we have smaller artificial neural networks, we have less training time, and we need less data for this. And less data means in some applications we are using only one single measurement. And this is a ridiculous little amount of data in terms of machine learning. So back to our pen ODE. So to conclude, for now, we don't see any proof. So this is just an analogy, and we assume that pen ODEs or NeuralFMUs combine some advantages of physical modeling and data-driven modeling, and they may even outperform plain neural ODEs under similar training conditions. But these are only assumptions. So yeah, I hope you're motivated now, because the only thing we further need to do before starting, or we do the coffee break and start right after the coffee break, is have a look on these libraries. And on the software side, we need three libraries from us. So the first one is FMI.jl. FMI.jl is to import FMUs into a Julia programming language. There's FMI Flux, which allows for building NeuralFMUs, so it makes FMUs differentiable and things. And under the hood, there are many libraries from the sciML ecosystem working together. So we have, that's not from sciML, but we have Flux machine learning. We have sciML sensitivity, difficult callbacks, and for sure a lot of differential equations. So at that point, thank you guys. I really love the spirit of this community. And yeah, if you find anything of these useful, leave us a star on GitHub. We're always happy if there are some new ones. And if you're interested in FMI.jl, we are currently doing a huge update. So there were many little overdue performance and documentation improvements, and after this we will do a 1.0 release. So one thing I wanted to show really quick, how many minutes? So I think 3 would be enough. Okay. So what I want to show you really quick is what is FMI.jl and FMI in action, because at the weekend I clicked together a little notebook for this, and it's called the FMU Explorer. And as the name suggests, it can be used to explore your very own FMUs. So we stick the required package because of timing, and you can pick any file you want. So sometimes you will have, in most cases, you will have a local FMU on the system. But we can also use everything that is shipped with the FMI by clicking here. And of course, we pick the FMU we are using for today, and this is the robot RR. Robot RR means rotational because it has two rotation points. So we load this one and see some FMU information. So where's the path, what is the file size, how much variables, inputs, outputs, parameters, and so on. So we have 211 parameters here, 6 states and 2 outputs. This FMU supports model exchange. So there's a check here. It supports co-simulation. This is basically the important part here. And we can simulate this thing. So we have model exchange. Model exchange means we can pick our very own solvable differential equations. Co-simulation means there is already an ODE solver compiled right into this model. So for co-simulation, you can't use another solver. It's basically fixed and compiled into the model. For model exchange, we can pick any solver. I need to admit that there's only 5 for today, but I make a little note that there will be additional solvers soon. So we can change the parameterization if we want. So we can click it the parameter and change the default value, but we don't want to do this now. We want really some records to show. There's some values to be recorded, so we can plot them. And I'm interested here in the TCP position X and Y. So this is the position of the robot hand. And yeah, after that, we can technically we could record every of the 4,500 variables, but this is a little much. So we just run the simulation and check out the plot here. So this should take maybe 5 seconds or something because pre-compilation. So here we go, and now we can see the values we wanted to record. Okay, so here they are. So blue and red is the position in X, position in Y. We have state events here, so state events are discontinuities. So they are at the very beginning and the very end some, and we have lots of time events. So this is every time we drive to a new point, we trigger a time event here. And this is a little more interesting if we change the x-axis, because we are now plotting over time. If we are plotting against the TCP position in X, we have position X against position in Y. And this is basically our paper plane. So this is a little more interesting. And we can do that, and we see, oh, maybe there's something written in there. This is only the position. It's not the line we are drawing. It's only the position of the TCP. But I think one can see something in here. And this said, I think it's a good point in time to get a coffee. Yeah, sure. Or ask questions.
Well, just a comment. I got a notebook run on Mac using Docker. If anyone's interested, I can share the Docker image or whatever.
Yeah, that would be really nice. So any other things?
I think I got it in Mac.
Yeah. So maybe get in touch with this guy. He knows. He's got a solution. So yeah, let's do the coffee break, and then we can start with the actual document. that's the thing. But I want to create process. I think it's a good motivation to say something. No, it's that leads to nothing.
Versus the outputs which are the conditions, right? Why don't we against the position delta position?
Nee, also ein bisschen schon.
Ah, here we go. Okay.
Yeah. So two guys.
So why did you screen against the delta?
So the difference.
Yeah, difference between because the positions are it's very noisy.
I'm not a big fan of this. So this training approaches for whatever. So in this time, many guys try to learn. I always error correction. So what the neural network technical learning is the difference between where I am and where I want to be. So, but this is like learning is this will often fail if you test it over very different trajectory. The model will just compensate the same state.
Yeah, so you're right. So if you the actual position and the neural network and you want the neural network, you can train it also on the delta between two generate the finite differences.
So like a little sort of a retirement approach.
Yeah, because I think that what we use is because it's training single neural network on positions, one is trade-off getting one bit wrong, getting the next bit right. But if you also train on the finite differences, like say two degrees, like first or second, maybe kind of things out. Basically, it comes down to exactly the same thing that the neural ODE does, but on the like legacy, traditional kind of old school.
Isn't this I hope I understand. Isn't this issued by non-equidistant prime samples? So is your
yeah, it is an issue.
So in this case, you need to train very specific.
First of all, the positions are not influenced by that, right? But the derivative is you do the finite difference. It's in a different time step.
But you're always dividing by the same delta.
No, you use the actual. I mean, you can use the finite difference.
Just right. Into the artificial neural network together with
You do finite difference kind of velocity and acceleration, and you train it across the whole
I think if you write this on paper, you will find something like you are doing the explicit order. So finite difference, all of that finite difference is very similar to
exactly.
You're right. So it's like solving a neural ODE with the explicit order.
Exactly, you're right. But it's kind of old school. It doesn't go into this whole neural ODE kind of differential equation, but it just uses the fact that you don't have to train on the actual signal, you have to train over all the functions. Any function on the output is trainable. So any basis on the complete output. So like the finite differences are just one function of the complete output. You can stuff out the outputs and train on them. Maybe I think it maybe goes back to the kind of old school regular supervised learning thing. It might be have like better software.
Yeah, one could do the little experimental production for this as well. Just another approach. to benchmark them a little bit.
Yeah.
Thanks. Yeah, sure. Yeah.
So if I call them modeling
I need to say that it's some kind of mix. So in some applications, so we put in, so there's the model from X to X dot, and then comes the neural network, which in this case manipulates the state derivative. But we are often using it. We are sometimes pushing in not only state derivative but also the state. So this way you have the artificial neural network that can do some kind of learning right hand side, but only, but also also the ability to correct derivatives.
So in the end, like from this approach, the ODE finally just gives us the derivative function.
Yeah, exactly.
Yeah, and then in some cases you just pass in the derivative from the FMU, and in some cases you pass the derivative plus the state, and you get the sign of.
So it depends basically on the use case, the boundary conditions, on how much we know from the system. And there's an interesting thing about this, because at the very end I will show you generic topology that is able to train for these connections. So you don't have to decide this in advance, you just can. It's a very generic approach. Throw the two models and say, check out how to combine them to get a good result. So in this case, you can put in state derivatives basically to the machine and optimize it to decide.
I have a follow-up question. So what I was trying to do is I had a which was like a paper machine process. The goal was to generate synthetic data from the was like Linux or Windows. I wanted to ask where we taking but in the meantime we are updating the parameters of the FMU and let it show like photos. So I'm trying to do this and say as a test you just have a model where I keep all the parameters.
So do you update the parameters during basically the run, or are you doing multiple simulations and for every simulation you use another?
No, the goal was to get it during the simulation, so run a bit. Change the parameters, so you run a bit further. So I can actually what would happen in the process. But then what happened was simulating for a few of these changes, and then in the end, after some time, it would crash because of I don't know.
Yeah, but the thing that is a little hard to debug is that there are sometimes issues. Of course, there are issues with microchip too, but there are also often issues with FMU itself. So the FMI standard, by the way, has a specific structure for this, because parameters in general are not setable during the simulation. But there's a special thing called tunable parameters, and which are. And yeah, it's always really hard to debug such things, because you basically need to have a look on the code and on the FMU itself to find out where's the problem. If it's FMU, or if it is by or need to debug this in the application. But if you got the application with you, we can show you. Yeah, no problem. Thank you.
So in the approach you just sketched, you kind of the white box part where you can model based on physics and then the correction part. If you ever use a similar approach to not only improve the results but also learn what was the deficit of your physical model?
Yeah. So this was one of the very first things. So we started this in 2021. So that was the first paper of this. And in this case, we also learned for a friction model, and you can basically cut off this artificial neural network afterwards and check for what is actually being learned. So if it's a friction model, you can put it in different velocities and check the friction force that is applied to the model. And afterwards, you can really use it to, so for example, symbolic regression to find some equations that fit this aspect. So this way, you can even use this approach to explore for the missing function.
Yeah, exactly. So you can learn because also maybe you're just missing all the equations. And then, yeah, related but differently, can you also use the same approach for parameter tuning? So when you miss some constants or you know the range is
exactly. And what we are always doing, I didn't say that in the presentation, but we are always, almost always, optimizing the parameters for the ODE together with the neural network parameters. Because there are sometimes applications where the error is just because you did some parameterization error, and it would be a bad thing to keep this failure inside of the ODE and now correct it with the ANN. So we are always, almost always, optimizing all parameters side by side, because this often has no influence on the performance, because we have maybe 50 parameters in the model and 5,000 we can add, so that's not an issue. But,
and FMUs are also ISP interface for that as well. It makes it easy to mark some of these as being.
Yeah, so parameters are declared. You know what ranges of parameters, and there are lots of possibilities. So you can technically you could write uncertainty, so parameter uncertainties right into the model description. So you say this parameter is uniform distributed between this and this. So such information can be part of the distribution. So you can really advance things.
And final question, because I was looking into some of this at some point. I remember then that there were quite some toolboxes that were part of the big part of JuliaCon.
No, I think there's so sciML sensitivity, things like that is still just. So everything we rely on. So our things are open source, so 100% flexibility will be open source by now because it's mine. And everything I rely on is also open source.
Yeah, I quite remember that.
Huh?
Speaker ausmachen. Ich habe meine Speaker ausmachen. Besser als meine.
Wir haben nicht den Vegetarier das Essen. Aber mir war nichts zu.
Wo ist das fette Schild? So bitte nur nehmen, wenn man. Vegan only. Und dich habe ich ein bisschen promoted. Schauen wir mal. Dann ist eine Pause für die Stunde. Soll ich mal weitermachen? Und ja. Jetzt kommt der Meister.
I just told them what
Thank you very much.
said that you were running out.
So how long is
Yeah, we can start already. It was 10 minutes.
long enough?
Yeah, so now it's long enough.
I have to do something.
Yeah, can start.
So let's proceed. Yeah, this was the FMU Explorer. This is part of FMI, by the way, too. So there's a Pluto notebook example, and one of these is the FMU Explorer. So if you want to check out your very own FMUs really quick, you can use that if you want. So yeah, I hope you enjoyed your coffee break, because now you have to do something, and it's the hands-on workshop part. So I hope you should sit in front of a precompiled Pluto notebook now, and if not, just give me a quick hint, so I will check for that. And the idea here is that you can explore the notebook at your own speed. So if you feel like it's a little too much, yeah, this is no problem. The notebook stays available after the workshop, so you can do it whenever you want. And if you have any questions, then don't hesitate to ask. So today is opposite day, and this means it's the other way around. So this is the topology of the architecture we will implement today, and you know it beforehand basically. So let's see why it looks the way it looks. So there are 3 little experiments to gain some knowledge of this architecture, and after that you can build your very own NeuralFMU and train it for a few steps. So the first experiment is on choosing the right signals between FMU and ANN. So basically you could use any of these 4,500 variables as FMU output and feed them into the artificial neural network. But yeah, that doesn't seem right, that's it. And the second experiment is we can't just do the FMU and the ANN together, so that's not possible. We need to do some pre and post processing. And what this means is shown in the second experiment. The third experiment, in the third experiment, we introduce these nice gates here. So that control how much of the original FMU and how much of the artificial neural network contribute to the hybrid model dynamics. So this is somehow similar to deploying a little flexible topology between the 2 models. And finally, we stick everything together and build and train our NeuralFMU. So let's check out the notebook, and we will do the very first steps together. So this is our Plural notebook. So there's the abstract. You know the abstract from the JuliaCon schedule. You know the introduction. So there are three things. There is some hidden code marked with this ghost here. This means this is code that is probably not interesting if you do the notebook for the first time, but it's fully self-contained. So every line of code that is executed is part of the notebook, and by enabling the cells with the ghost, you can check for the entire code. Some computations are disabled for performance reasons, and these are marked with this info icon here. So this is the training itself, of course, because training takes some time. You don't want to execute this automatically. And yeah, these are activated by checkboxes, and these checkboxes has this action icon in front of them. So there's an example video. You might know this one from the slides. There's a list of requirements, but every one of you attended the introduction, so you are well prepared for this. And there are some technical requirements, so 8 GB of RAM it should be, but 16 would be nice. Windows and Linux should be supported, and technically, I think it should work down to 1.6, but it's tested on 1.10. So if it's possible, use Julia 1.10 for this. So we start by loading the required Julia libraries. And this is Pluto UI for this Pluto notebook, of course. As I told you, it's FMI to load and simulate FMUs. It's FMI Flags to do machine learning with FMUs. It's FMI SU, which contains the FMU we are working with today, and also the data, by the way. Then we use Flux, but Flux is part of FMI Flux, so we can use it, import it using FMI Flux or Flux. So I hope every one of you knows Flux, so the machine learning framework. And for sure, we need differential equations to get these things solved. And there's a little additional thing. It's just progress logging to show progress bars in Julia. It's benchmark tools to do a little timing benchmark. And you need plots and plotly.js to get some interactive plots. If there are any issues with plotly, because we have one system, I think, then just raise your hand and we switch backend here. Yeah, and there's the first hidden code section, so we can check what is in here really quick. So these are only some messages to print. This is some execution configuration. This is not important for now, but I just wanted to show you that there's the possibility to check every line of code that is executed in the background here. So we start by loading the FMU and the data. So data can be loaded using the FMI SU. So there's this command FMI SU.robot.r double point train. So this means giving the training data for today, and we can check this data train object. There are some points in time. There is a TCP position X, so TCP is, by the way, the 2 center points, so the hand of the robot. And there's the TCP position Y, the velocities, and some other interesting variables we will use today. And yeah, the nice thing with such a system is that we can do a good visualization for this. And now we check out the training data. The training data is letting the robot write the word train. So this is our training data. And what you see here in red is the robot base. So the red dot is the robot base, and this is the first join basically. This is the second join, and this is the TCP. This word train is from data. This is our trajectory submodel. So this is what we want the robot to draw actually.
How did you obtain this?
It's from our high fidelity simulation. So the word train is by me. So I decided this that we want to write train today and validate for validation, by the way. And and the trajectories from the high fidelity simulation. So we just loaded this one. Exactly, and now you can use this little slider here to start drawing. So first thing is, so this is the first second. The first thing is we drive our TCP to the start of the word. So there's nothing drawn yet, and after I think 3 or 4 seconds we start drawing. So this is just visualization basically. So we are doing just a little nicer visualization. And so this is the first letter, so we can zoom in on the T. And yeah, well, it's not perfect. So black dashed is where we want to be, and green is our actual line. But yeah, if this would be a real system, it would be quite okay, I think. So at least it's for me. And yeah, so let's check out what happens if we draw a little further. So there's the A and the I. So the dot on the I is a little weird, but it still looks okay somehow. But if we do the full writing, there's something very weird happening to that N right here. And this is basically because we are now much further away from the roller base. So the translational force that we can cause with a motor torque is much smaller if we have a long level. So the frictional force of the pen is 2. The frictional force is always the same, but the translational force we can cause becomes smaller the longer the level is. So here we see that we have the slipstick friction. So the difference is, as long as we are very close to the roller base, we can cause very high translational forces because we have the full motor torque for this. But if we have a really long level, everything becomes a little more fragile. So, and this is what we want to reach with our simulation model. So we want a very accurate prediction of what is happening in the real system if we try to write this word here. And yeah, I think the rest is up to you. So from here on, I'm just here to support, so you can explore it at your own pace, and I'm here to support, of course. So there's now the hands-on part, and half an hour before this slot is over, we will have a conclusion, conclude some results, do some summarizing, and have a look on how this journey can go on. So it's up to you now. Yeah.
Sure, I cannot get the works road already. The first Windows.
Oh, that's a good stuff.
Yeah, already tried it a few times.
Oh. Then can you see that's actually so yes. It's the same error than so you just have to change at the top of the maybe just or just I think you have to change so you do basically here, you just remove this, so you can and calls you are, and you get to Yeah, I'm not sure if that's automatically.
Then you just run it.
So now you just have to change this line is GR into small letters. So now say that they
Just do the same thing.
and somehow there was exactly the same. It's about compilation of and at some point the package gets removed. The problem is that the package creates a temporary file for calculation. That temporary file gets deleted and that is the insertion error from this file. There is no file. Yeah, you're correct. Yeah, it depends on the point of view of the system. Okay, so inputs in this case means really inputs that need to be sent to get this system simulated. In our case, we call trajectory was a subsystem. So the system boundaries is a large everything we saw in this picture. It's a system with zero input because the trajectory itself is part of the system. So this is the reason. So if you cut this trajectory subboundary and then add external inputs for this, in this case, okay, right, that makes sense. So that means here the input, the jerkily signal is kind of already. Okay. So, yeah, it's a fully so, but you can, so one last thing, so you can, of course, change by changing the string parameter that contains the path to the file that is during the simulation. So, for example, exactly right. This is just replacing one parameter that contains path to the trajectory file. So this way we can change the features. This is just a question where you draw this right. The goal is kind of to model the right? Yeah, exactly. Yes, this is here. It is already containing the input data, the output data. Sometimes it's nice thing to be able to say where this deviation is coming from. So unfortunately, now it's if I give you just the data, you cannot say where this deviation is coming from. So it might be parameterization from number assumptions and substitutions and perhaps it's a mix of multiple sources. So for academic purpose, sometimes yeah, I think it's totally okay. Okay. Yeah. Okay, and example ist Pluto Source und dann ist das ist das And all the same, if you visit Mikelsons, if you want to save this, you can just give me which one? Oh, okay, sorry. Hey.
I had a question.
Yeah, sure. Oh, that's so good. Oh, yeah, I know the trouble.
Okay.
So I think, so can you scroll up the line there that FMI using this? So using FMI that there is a version 1.0.
Yeah.
So this is, I cannot explain this very good because the idea behind Pluto is that we have a specific fixed version for everyone. And I fixed this version to 0.33.
Okay.
For some reason, you're now on 1.0, and I think this is maybe because there was some update call. So were there any issues during the pre-compilation?
No, I don't think so.
So the good news is I'm pretty sure that you can fix this by if you just scroll up to the Julia.jl icon. So this should be fixable just by killing this thing.
Okay.
And start it. So insert the URL one more time. So pre-compilation should now be much faster because there's already something pre-compiled.
Yeah.
But if something fails during pre-compilation,
then it goes up the.
Then it starts updating it. And I don't know why this is. So this shouldn't be the way it is. But this,
yeah.
I'm sure that this will fix it.
I'll try and then thanks.
Thank you.
Were you mentioning something about the pre-compilation?
Hey, I didn't see you.
There's a version of me in every group.
Yeah.
We just mentioned something about pre-compilation triggers.
Yeah, exactly. So we can do this that we can fix the word, which is a quite nice thing. So I fixed the FMI to 0.33. And now I saw a notebook where it's on 1.00, which is not compliant. So it doesn't work. So we get issues. And sometimes, so at least for me, it feels like if Pluto starts recompiling and something fails, it triggers a new recompile. but does an update beforehand. And this way we are going into wrong versions, which is really annoying. But if you're facing this issue, so where it says there's no FMU robot RR, you can just restart and also in this way it should work after that. So.
You didn't know that would cause an update. Have you had engines?
No. This file is very new for me too. So it was yesterday. And I think I tried it by doing something.
Yeah. That seems like it should be. I thought you were mentioning something. I was
It's all it's back again.
The thing for instantiating an environment, they can charge it should be fixed as like the last 2 weeks stuff. So it's seeing a lot less freedom.
Yeah, okay, good to know that. Ja, interessant, dass es dann doch irgendwie woanders angefangen.
Ich meine, dass ich den Support so genau das temporary files.
I'm on my way. Yes, exactly. For some reason,
yeah, it might reduce the board that's so if you run this command of the run, then it will basically just start and the log will be this.
Yeah, I'm getting hungry. It's also about theoretisch soll ja jede Zelle durchlaufen. Genau, theoretisch sollte einmal alles durchlaufen. changes. So, which of one was the first? So maybe we don't just so those are so there's some exactly, that is the model where we started. So I always the data, so there's run through data from simulation model to simulate. So there's I'm not sure if you tunable parameters I think for this Exactly, and that option should also Hey, they are in part for so if you go on this workshop, there's slides here. There's this URL and there's also the presentation slide. So I think you can check this page. Okay, sorry for that. So it's very well. And you need to kill Pluto and then insert this URL again, because once it updates on 1.0, you have a local copy of it which says 1.0 and this is correct. So you need to kill it and reuse this URL, so it will have it's checked out. No, not Pluto, just a notebook. This is a TCP position, as also the the panel position basically, the two center point, in direction X and Y in the world for the whole. So if you view this the system from the reading from above, in the position of the robot line. And this is, by the way, the thing we often during the Explorer. Okay, this is just a yes. So this is no, it's not a form that's a union 22 that identifies, uniquely identifies the variable we are talking about. So in FMI there is a thing called model description, which is a catalog or model identifiers and that's it. So it's the unit 32 of this number. So if you want to know to plot a little, it's maybe so but this is interesting that the plot struggles to plotting a single. Yeah, I see that could lead to confusion. Yeah, but maybe we should open an issue for that. Because it should throw some error or something, so that just printing one number is not possible. Yeah, it's maybe it's a unit. They can use it. So maybe it's just an issue. It's a unit. We are going in a very weird route. Or maybe it's this specific number. This is very. I don't know. Okay. Very high. Yes. Oh no. Yeah, like because with this export, so it's export parts of export everything. Your process is exactly make much sense because like it's only something. So in this situation, we have not publishing all of the steps we are touching this. So we are interacting with what outdoor cars, and this is why short-term I can't even exactly because so this is quite small, it's 6 states. But if you think about the large almost in any case we don't want to touch the states because there are always some things where say, okay, this is right, it's the mechanics part is okay, but these electrical states need some correction. So you in almost any case you split the state space a little and only manipulate. Yeah, you only manipulate the power when you inside all the things. I'm not sure about So when see the package, if you check these boxes, you change not quite. Currently, these are already checkboxes are just there. We want to add additional ones, but in this example, exactly. For additional ones, you don't have to add it. Just ask me.
So they're redundant.
This is the
We don't need to adjust because they're already.
yeah, this is the experiment.
Here you add like.
So like a better. Don't do it. You can, but it's not a better.
Yeah, maybe it,
Yeah, you should find the emissions.
yeah, if I have
Yep. Oh, yeah.
Es gibt alte Pakete.
Soll ich da was sagen? Ich glaube, der macht einfach, wenn der hat einen Try-Catch und wenn der fehlt, dann macht er ein Update, weil viele Pluto-Notebooks failen halt, weil sie veraltet sind, weißt, weil sie halt einfach 2 Jahre alt sind, die Versionen immer lauffähig sind. Dann macht er ein Update und probiert es neu, weil es ja quasi, wenn das fehlt, dann liegt es wahrscheinlich daran, dass die Version immer passt. So. Genau. Also der Handelsüberprüfungskurs, der macht ja zum Beispiel und danach alles auf eine 1. Also wenn ich eine 10 reinwerfe, kriege ich eine 1, wenn ich 10 Milliarden reinwerfe. Das heißt, wenn das ist tatsächlich eine Prüfung, wenn man jetzt wirklich Bausmodell ist, oder wird das alles gesagt. So, das wäre jetzt, also es gibt verschiedene Ansätze, ich sage jetzt mal, die sind aus einem zum Beispiel Ansätze, wenn man es jetzt mathematisch korrekt angeht, dann das Normalprogrammation, die Shifting-Scale so, dass ich normal möglich und dann meistens ist es so, dass wenn man jetzt hier zum Beispiel ansetzen würde, dann trotzdem diesen ersten Ausschlag mit dabei, weil das ist halt nur ein Ausschlag, der am Ende des Standardverfahrens so viel, dass es dann zum Tragen kommt, deswegen ist es dann händisch und kleiner Diskussion, das ist immer ein bisschen im Prinzip hat das ja eine Einnahme, das zu klein, das ist das ist man ja so militärische ansonsten ist es ganz gut. Und Ziel ist halt deswegen man das als ist halt so ein Text, klassisch. So, genau, das ist quasi, wenn man den Zugriff einmal posten, dann schauen, was kommt. Und idealerweise, sage ich mal, das ist ja eher blau. Wir wollen ja das Blaue mal so, was wir haben. Wir wollen eigentlich schauen, wie man wieder dazu hinkommt. Genau, das ist tatsächlich das, was man das ist auch genau, und da ist es aber ganz beruhigt, das wird mehr passiert, als wir uns jetzt, also ich habe ja Then that's one story. Genau, das ist etwas Neues, kein Instrument und dann das Gesamtding, das bauen wir dann später. Genau, also die sind tatsächlich bei diese Experimente, die sind zerstört und ganz sinnvoll zu machen. Ja, das ist halt auch yeah, that's my favorite. So the idea is the structure of the there, and there's already there, like it says, the whole thing is right there, and it's just guiding you to the different. So the assumption is that okay, we expect the first part, the FMU, and now we'll talk about the next part. But it's already there. So we get started already about yeah. So it's like we start with a model that makes that prediction on itself and try to do that. And then all of this goes into the integrator with the data. So I agree. it's a second line.
That makes sense. But then, so your data structure batch is basically assigned to the result of and the selector will multiply the start.
Yeah.
Batch, a single batch is a whole.
So the batch is the entire stack that is stored, and batch elements are cut off. So it's very short. Yeah, so it starts from 0 to 5. Yeah, exactly. This is because the grading becomes very expensive. It's often target oriented to the entire system because if you make if you have the gradient for the entire trajectory, just forcing thread to be met. So it's like how to reach this level approximately. So smaller batch elements are actually going on dynamic. So the things that happen. So this is
So let's say I choose 0.05. That each batch is going to be a 0.05.
So yeah, that's batch containing 100 elements in every one, and then
So that's the data.
that's the simulation.
The simulation is also even more finite. That's what you are taking up. And so that there's a lot of different like long and short term memory
Yeah, at some point, gradient information is this level we will refactory. So there's nothing, there's no details in it, just one key, but the way it's by the average or so they don't do consistency. So they just put it straight right to So let's have a look on the possible outcome of this workshop. So we had this weird introduction on scientific machine learning and hybrid modeling, and leaving us a little alone, we're confused with two questions. And these two questions were what is the hybrid modeling foundation made of, and what is the scientific machine learning, scientific computing crane over there? And this is only one possible answer, but this model foundation may often be some physical simulation model. So today it was a functional model in it. And this crane from scientific computing was for today a ODE solver as we use it in NeuralFMUs. And maybe tomorrow it will be something different. So I concluded some findings from during the workshop, and the first one is we need pre and post processing if we connect physical and machine learning models. So this is because we do have different operation ranges for the physical and the machine learning models, and we can do a rough initialization for that pre and post processing, and then train these parameters together with the parameters of the artificial neural network during training. So we can even adapt to changes in the input range of the example. So we found that these gates allow for more flexibility in the architecture. So we still maintain explainability of the model. So it's super intuitive to say 30% is coming from this and 70 from the other signal. And we discussed at the very beginning, so this was actually the first experiment, we discussed that interface design is quite important. And so if there are too few signals to connect to connect the FMU and the ANN, that's an issue because the important information might not be there, and that is for sure bad. But if we connect to many signals, and the training is unnecessarily intense, so in terms of computational performance. And yeah, there's another issue, and this is that there's an increased risk of learning for non-causal relations. So if you think of, you have two very similar signals, and one has a causal dependency on the thing we want to learn, and the other one not, then the ANN could learn for the wrong one or for both, and we definitely don't want this. And yeah, we can tackle this, however, by using more data, but using more data is not always an option here. So what are the results of the experiment from today? So let's check this out. So we start by checking the training results. So this is where we wrote the word train, and this looks nice for the first moment. The blues, in blue there is the NeuralFMU, in orange there's the pure FMU, so the model we started with. And we will focus on two letters. So the first one is the A here. So the A isn't affected by slipstick friction very much because it's very close to the robot base where we have high translational forces. And then there's the N, and the N obviously knows what slipstick friction means. So we picked these two different letters, and the main difference is indeed the distance to the robot base. So on the A, we have a maximum fit. So the NeuralFMU here is in blue, and it's almost perfectly on data, and data is in black dashed here. So it's barely visible, the data trajectory. So the original FMU was in orange, and this one has a little offset. So there's sometimes we are a little too low, sometimes we are a little too high compared to data. So on the N, we are also much better than the FMU. So we see that the slipstick is understood quite good here in blue. And the original model, so the original FMU here in orange, just ignores that oscillation completely. However, we can also achieve a better fit here if we train this a little longer. So this is training data. Training data is a little boring, so let's check out what happens with validation data. So this is important because think of this ANN example from the introduction. So validation data is important. Let's see how the word validate looks like. And also this word at first glance looks quite good. So we will check 3 letters here. So the first one is the D, but D is very similar to A. We check for the T, and T is interesting because we know it from training, but during the training it was the very first letter, so there was no slipstick in it. Now we have it with some slipstick. And we will check for the letter E because E is completely new, so it's not part of training data. So as for the A, the D is very nice. So there's not much to say here. The NeuralFMU in blue has a very good fit regarding the data trajectory like dash. And the FMU is in orange here. So the T is the letter we know from training, but not with the slipstick friction, and even the T has a relative good fit. And one can see that there's like this little phase shift here at the end, but it's definitely much better than the original FMU here. And there's finally the E, which was completely new, and we see that even there it's really nice. So what I really like about this is that there are two very different types of correlations. So for the D, so some very different types of corrections. Sorry. So for a D, we have like this offset correction where some values are a little too large, some values are a little too small. But for a T and the E, there's something completely different. There's this oscillation on it. So two very different things that are happening. And yeah, this is, in my opinion, a really cool result for this one. So now, because I promised at the very beginning, one important question remains, and this is, does this only work for the SCARA simulation model? And the answer is no. We're using this for very different applications with similar workflows in different application domains. And I brought some examples. So we will do these real quick. So let's talk about this in detail if you have any questions according to this at the conference. So the first is an hydraulic excavator arm. So for mechanical systems, often the friction model is the part that is the most difficult to model. So this is because very easy friction models are not accurate enough, and very complex friction models are very hard to parameterize. So we tried learning a friction model in this case. So we started with a very simple viscous friction model and learned based on this. And because it worked quite well, we tried it based on a frictionless system. And this is the trajectory here in blue. So this is a system without any damping. So from a technical perspective, it's a border stable oscillating system. And as you can see, that worked quite well. So NeuralFMU here is in green. And the interesting thing about this use case was that before NeuralFMU, they tried many other AI methods on this, and they all failed because the ODE properties here are very messy. So the second one is from an entirely different domain. It's from computational fluid dynamics. It was in the medical domain, the simulation of the human cardiovascular system. And this was, I think it was my very first use case I did with this approach. And the goal here was a little different. It was to increase the simulation performance. So we tried to hold some accuracy, but needed to improve simulation performance. So we started training based on a very simple steady-state simulation. It's the one in black dotted, and this steady-state simulation is that bad that I needed to cut it off the plot. So this is a very rough simulation model, and we trained it to fit the arterial pulse waves, which are in red here. So this is data from the CF full-scale simulation, and we tried to fit that data. And the result was that we could match the accuracy requirements, but I think it was around factor 3,000 faster for inference, which was a cool success. So this is some kind of a hybrid surrogating application. So we also did it for a consumption model. So this was the consumption estimation for an electric Smart 4.2, which is shown in these two plots. So the right plot is the more interesting. It's the very same as the left, but it's a little zoomed in. And you can see that the NeuralFMU, which is in green, almost exactly lays on the measurements, so which are blue. And this, by the way, validation data, of course. So this is not training data or something. We were even featuring higher velocity profiles during validation. So we trained, I don't know it by heart, it was around between 0 and 40 mph, and we drove 60 mph during validation. So this was including some extrapolation. So more details about this is because this was a use case from last year's workshop, are in the slides from last year or in the digital review from last year. So check out this. And this is the last one, but my very favorite. Even if there's not much to see, this is an actual simulation model as it is used in automotive engineering today. So it's a simulation model of a fully controlled easy motor within the electro-hydraulic braking system of a state-of-the-art car. And this is super messy, it's highly nonlinear, it contains a sample subsystem, and it triggers at least 10,000 discontinuous events per second. So it's a super messy simulation model. And by the way, it's also border stable to make it full. And as complex the system was, as easy was the job description here. So the simulation was not accurate enough to do hardware and software in the loop testing here. And so we need a more accurate simulation model. So that was the job description. And the bad news is I can't share the plots, but I'm allowed to share the average errors. And one need to say again that the model we started with was already very accurate. And yeah, after training, we had, for example, three times more accuracy on predicting the motor angle during a braking maneuver, which is a super cool success, because if you tell your boss that you increase the model accuracy by 30% in 1 month of work, you get a raise for that, because that's a great success. But if you tell your boss that the new model is 3 times more accurate, he just won't believe you this. And yeah, this is, by the way, also all on testing data. So we neither used it during training, not during hyperparameter optimization. So to conclude, this technique is not limited to electrical or mechanical or biological systems. It's as versatile as dynamic systems modeling, so it can be applied to a huge field of dynamic systems. So this is my little final for today. We could talk about where the journey is going, and this workshop had a strong focus on architecture design. So we talked about how can we connect physical and machine learning world, how do we need to transform the signals, and so on and so on. So if we check out topology one last time for today, we talked about that pre-processing is necessary, but pre-processing is just a linear equation. We talked about that gates are helpful, but gates are just a linear equation. We talked about that this concatenation or merging of signals here at the very end, we did this implicitly before numerical integration, is also important, but this is also just a linear equation. And now connecting these blocks all with each other, so inputs to outputs, is nothing but the most easiest linear equation ever. It's basically y equals u. So let's remove everything that's linear for a moment. And the only nonlinear things that remain here are the FMU. So this is a nonlinear thing in general, and the ANN. So if we have the nonlinear activation functions, they are nonlinear. And because it doesn't matter if this is an FMU or an ANN or just an ODE, I just call it AED for now. And to keep it easy, we are doing some simplifications. So we are neglecting discontinuities, we are neglecting explicit time dependency and things like that. If we now build a big vector of inputs, so a vector containing the inputs from system A, so UA, this is the inputs from system B, so UB, and the inputs from the hybrid, from the resulting hybrid system, so we use that. And do the same for the outputs. We have 2 new vectors, and now describe all the linear equations we had in just one single one. And this is this. Because everything was linear, we just showed, this new equation is able to express things like pre and post processing, and also things like gates between any possible signal combination of inputs and outputs here, only based on this scaling matrix and this shifting bias. So Why should we do that? Well, because we can learn for that thing. And this means we can train for arbitrary connections, so arbitrary connecting architectures between our two models. And this means there's actually no need to think about architecture design anymore. And this is super nice, but there are two little things that must be considered. The first thing is, it looks like we are losing a little bit of interpretability, so explainability suffers a little, because looking at such a matrix, yeah, it's not very insightful for human beings, at least for me. So, but we found their structure in it. So we can divide this matrix into 9 submatrices, and we find patterns for a parallel-like topology in it. We find patterns for a serial-like topology. There are 2 cases. So A is evaluation for B and B for A. We have patterns for direct feed-through between input and output, and we have patterns for self-connections. So if we put the output of system A into the input of system A, for example. So for now, this is at least some interpretability. The second issue is if we take this full matrix learnable, so the full matrix, every entry of it, there is a catch, and this is we built in a lot of algebraic loops in our system. And this is, yeah, this is technically not an issue for a mathematician because you can apply Targent's method to find them. Then we can do some reshuffling to reduce them. Then we can do some tarrying and then iteratively solve it applying Newton's method. But we need to do this online, so we need to do this during training. This is a waste of computational performance because you need to consider that we build in new connections leading to new algebraic loops, and we are resolving connections that leads to resolving of algebraic loops. So we need to do this online, and this is a lot of computational performance. So, so it would be really nice to have a topology that does not construct algebraic loops, but allows a little for training these different topologies. And there's one, this one I call the loop-free architecture, and this is designed by step 1, self-connections are not allowed. If you think about an artificial neural network, so if you follow an artificial neural network and you connect, this is by design an algebraic equation. So if you now connect the output to the input, you have an algebraic instantly. So this allows for self-connections. And the second thing is, we put in an OR here. So we only allow for a connection from A to B or from B to A, not both at the same time. Because if we go from A to B and from B to A, we don't know what is inside of the 2 subsystems A and B, and therefore we could not say that there's no algebraic loop. So we disallow for both serial connections at a time. And yeah, these are the 2 loop-free architecture patterns, and yeah. For the resulting patterns, one can prove that these are free of algebraic loops. You can do a structure incidence matrix, a block-lower triangular transformation, and show that these 2 are by design free of algebraic loops. And yeah, this is a really cool thing because now we can train with these things without constructing algebraic loops, only by disallowing a little bit of the freedom we have right here at the top. So now, what about this interpretability issue? So this was an experiment with a 2-dimensional bouncing ball. So this is a ball in a cage. So we have 4 walls at the top, at the bottom, at the left, and at the right. And every time we hit the wall, there's some energy dissipation, and the ball gets reflected. So this is basically the trajectory we see here. So we start here at 0 seconds, and it goes bounce, 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 and so on and so on. So after training, we had a really good fit here. So the details are not important for now. What I want to show you here is that the matrix or the submatrices we learned can be visualized by plotting it. So black values are connections close to 0, so something like no connection actually. and the y values are close to 1, so like a straight connection. And all of these matrices can be interpreted in two ways. So first, because almost every one of them displays a connection between a machine learning model and a physical model, we see what signals are connected to what signal of the machine learning model to the physical model and vice versa. And we even have physical units, and that makes interpretation a little bit more easy if we have a physical unit behind. And the second case is we can group these submatrices regarding their role in the architecture. So this way we can understand if there are any of the patterns we just saw on the last slide, for example, are present. And yeah, I have a little example of that for sure. So this is the pattern for the parallel structure. So for the parallel structure, we're just having a look on these four matrices and check occupancy of these four. So to keep it short, it's not perfect identities here. So the right middle one, so it's WZ, and you have good eyes. We learn for a linear combination of signals, but this is fine. To keep it short, we find that this is something like a parallel structure in here that was learned. So this is the second thing, it's a serial-like structure. For the serial structure, we only check out these three matrices. And yeah, we find that there's a serial-like structure in it. And if you're wondering this matrix here, because there are only two fields occupied, is because we manipulate only the acceleration of the system. So it's a second order ODE. So with position and velocity is state, velocity and state derivative, velocity and acceleration is state derivative. And we are only interested in manipulating the acceleration, of course, otherwise we would disintegrate our second order ODE. So this is the last thing, it's direct feed through. So as you can see, we don't or almost don't use direct feed through. So this is almost like this matrix. So as I said, one could check all of these matrices in detail and discuss them, but that goes too far. But feel free to catch me and let's have a discussion on this. So I uploaded a preprint regarding this complete thing to archive. It's called Learnable and Interpretable Model Combination in Dynamic Systems Modeling, and it's also linked somewhere in the notebook, I think. So wait, what? That causes somehow mixed feelings because we built a quite specific topology today, and now we concluded that this is also, it's also possible to keep the entire architecture flexible and just learn it. So does this mean that everything that we did today is outdated? And of course not. It's always a trade-off between different things. So first thing, it's a trade-off between explainability and flexibility. So if we have a very static architecture, is based on some logical thinking. So, static architectures can be understood very well. So if we keep the architecture more flexible, there is less to interpret in it. In this special case here, we use these linear equations because we can easily visualize them. However, if you think about these gates, they're super intuitive. So there's nothing more intuitive than saying 50% is coming from here, 50% is coming from here. So the second trade-off is the amount of data. So more degrees of freedom for our model means we need more data. But to keep it short, there will always be applications where we just don't have enough data, and so we don't have enough data to use these most generic approaches with very large parameter counts. For example, this bouncing ball, the example of this bouncing ball. we trained this one time on a static architecture. So with a very static architecture, we only needed one single measurement trajectory to get a good fit. So to understand the nonlinear air friction, things like that. If we apply the loop-free architecture, so the flexible architecture that we can train for, we needed at least three measurements trajectory to have a good fit and not learn for uncorrelating signals. So even for this very simple example, we needed much more data to get a good result. And the third thing is, yeah, if we pick a suboptimal architecture, and this is not unlikely for a human being, then we may need to relearn some parts of the model. So for example, think of you have coordinates in the wrong coordinate frame. So this is easily imaginable for robotics applications. If you have coordinates in the wrong coordinate frame, you basically need to learn for the coordinate transformation. And this is redundant work. So things like these happen if you do this interface by hand. But on the other side, there's the big win, and this could be that we find an architecture that's an optimal architecture that we might not have in mind as simulation engineers. So this way we can optimize for it, and we find something really cool. Yeah, so both keeping an architecture more static and keeping it more flexible has advantages and disadvantages, and therefore everything we did today was good. So I really hope that this workshop will help you with your very own scientific machine learning and functional mobile units and hybrid modeling applications. There is still work to do, so we are working on making things faster and more stable under the hood. So as I told you, there are some modifications we need to do in FMI.shell and FMI.flux.jl, some implementation and also some documentation things. And there are still multiple challenges on the research side too, so machine learning industrial models. It's still there's still something to do, and we also started a new research project on this. And that's it from my side. Thank you very much for participating. I had a lot of fun, and I hope you enjoyed the workshop too. And just let's have a nice talk at the conference, and you can send me an email, of course, if the conference is over. And that's it from my side. Thank you.